Well, looks like we're just about there. Any questions at the moment, folks? Hey, it's time. Welcome back, everyone. Looks like we could get started. Before we start today, I want to go through the announcements, but I don't think I really have too much to say. We're getting through section 4.3. That's going to be the last section on this assignment right here. There's not as many problems on these as we've seen before, like when we were calculating derivatives, but that's because the derivatives were really fast. These are slightly longer problems that we're getting through here. We're going to look at issues of how to find local minimums, how to find local maximums. We're also going to be looking at how to determine a concavity of the curve, whether a curve is concave up or concave down. But it'll be pretty similar stuff to what we've been doing in either one of these sections, just slightly different topics. But in fact, the real thing we're doing right away is pretty much we're going back to, not this, let me try again. We're going back to this right here. We're not trying to sketch the derivative. To me, that's pretty hard, actually. But we need to have information of what the derivative is really doing to our graph. So returning back to this picture here, always remember that the value of the derivative, f prime at x, is always equal to the slope of the tangent line. The slope of the tangent line is also telling you if the function is going to be increasing or decreasing. So say for here, the slope is 0, the function is at rest. It's neither increasing nor decreasing at that point. But over here, the slope of the tangent line, it is positive. That means the function must be increasing, which we see on the graph. So wherever f is decreasing, the slope is less than 0, but that means equivalently, the derivative is less than 0. We're pretty much going to reproduce this sine table right here, talk about the derivative, and we'll find out where our local minimums and local maximums are using this information. So that's the main idea. And here are the new tests. Oh, that's way zoomed in. Probably doesn't need to be zoomed in that far. So the increasing decreasing test is kind of just saying what we said all the way back in section 2.8. If we have a positive derivative, then f is increasing on that interval. But if the derivative is negative, it must be decreasing on that same interval. Let's draw just a really fast function to see how that could go. I want the function to start at a point. It'll begin just by going down, coming back up, and let's make it stop, say, right here. So just a weird looking S-bend. So if we look at this, we have two spots where the tangent line is going to be horizontal. There'll be one spot right here. That gives us a value, let's call it, say, we could call it maybe C, because that would be a critical number. Let's maybe call it C1, there's two of them. We could say over here, f prime at C1 is 0. Then the next place where the tangent line would be purely horizontal would be way over here. We can call this one C2. Likewise, the derivative of f at C2 would also be 0. So that makes these both critical numbers. But now let's look at the increasing decreasing test once again. If we're over here, what would you all say the sign of the derivative must be? Is that a negative derivative or a positive one? Good call. This one would be negative. And if we put a tangent line on this, that tangent line would have a slope that's negative since it's going down. And so we can say all the way in this range, let's use a color that just seems more important than the comment pen. Oh, this is tricky. Let's see if I can zoom in just a bit. Let's scroll just a touch. There we go. So from here where the curve started, all the way to here at the first critical number, we can say f prime is negative, but also at the same time, f is decreasing. I'll use DEC as an abbreviation for decreasing. Then going from here all the way over to C2, well, now to have a positive derivative, the slopes of those tangent lines are also positive. And f is increasing. I'll just spell this one out. We can fit it this time. Then likewise, from here to here, oh, that's a little too far. The domain ends right around here. So on this tiny portion, we have, once again, any tangent line here would have a negative slope. So the derivative is negative in this region, f prime less than 0. And that means f is decreasing. Now, once we have that sign chart, we're pretty much done with the increasing, decreasing test. It's kind of silly on a graph, right? Because we know it's increasing or decreasing just by reading off the graph. It's still a good idea to do this because on the coming problems, there's no graph. So this is our opportunity to tie together information about the derivative and whether it's increasing or decreasing. It's also our opportunity to take a look at what is the first derivative test going to tell us. The first derivative test won't just be used in this section. We're going to use it again in section 4.7 when we're dealing with optimization type problems, where we're looking for maximums and minimums to real world applications. It says, suppose C is a critical number of a continuous function f. We have two critical numbers on our graph, C1 and C2. So that means the derivative is 0 or the derivative failed to exist. And you know what, I forgot, I kind of did want one that the derivative did fail to exist right here. I'm going to change the curve just a little. Oh, geez, I have to change the whole curve. I'm going to change the curve just a little bit. I want to put a sharp peak here just to convey, yeah, the derivative did not exist on one piece, since that's always still important. So let me try one more time with this curve. It's going to come in through here in a nice smooth way. But then right here, we have a cusp. Definitely that's allowed. And notice the derivative only failed to exist at C2. I need to change this line right here. So we have f prime at C2 does not exist. Making it the second version of critical number. But out here, the derivative does exist. It is positive and it's still increasing. Over here, same issue. It's just decreasing and the derivative is negative. Oh, didn't mean to track that point off. Gotta be careful clicking on these things. So now we're ready to go. Let's take a look at the first derivative test. It says if f prime changes from positive to negative at your critical number, then you have a local maximum. Looking at our graph, we have a local maximum right here. Let's look at the sign of the derivative. It's positive in this region. At the critical number, it doesn't even exist. But then when we go to the opposite side, it changed to negative. So right away, we can read off a local maximum just from that information. Does that make sense to folks on how we're finding it? Okay, let's take a look at the second version here. Part B says, if f prime changes from negative, that's happening right here, it's negative, it's decreasing, to positive at a critical number, increasing here, so it's definitely positive. Then you'll have a local minimum. And yeah, that's a local minimum on this graph. In fact, it would be also the absolute minimum. And this would also be the absolute maximum. The content of the theorem is all about local minimums or maximums, and we'd have to infer if they're absolute or not by further information from the graph. So that's what happened so far. And this one here says, well, if f prime does not change signs at the critical number, we'll have no local maximum or minimum at that value. Now, that one's always a kind of a weird graph. We did do one, but this happens when it looks like this. If your curve does anything that comes around like that, that's when this is happening. There's still a critical number. If this is y equals f of x, then f prime at 0 is 0, giving us a critical number at 0 itself. But we see that it's increasing and then increasing again. The derivative did not change sign, and so there is no maximum or minimum, as we can also see on this graph here. So that's the content of increasing, decreasing test. This is really review right here, but it's good to bring it back into the problem. But the first derivative test is the bigger result, tying in the prior information. Well, any questions, folks, before we try it with an algebraic version? Okay, let's give that a try next. Some of the derivatives in this section, they're really not too bad. And this one is kind of a break in a certain sense. We have a degree 3 ordinary polynomial that we're going to crank out. On part A, we want to find the intervals where f is increasing and the intervals where it's decreasing. So in other words, we're just using the increasing decreasing test right here. Whenever we go to use that test, as part of the work, we have to write out a sign chart in some way. It doesn't have to be with an interval using the brackets like we're about to. So if you have a different way of producing your sign charts, then that's going to be just fine as well. But we have to show the information indicating positive or negative on our derivative. So here's how this one's going to go. The very first thing you want to do before you determine where f is increasing or decreasing is you have to find the critical numbers. Notice that's where it splits, where f is increasing or decreasing right at those critical numbers. So let's begin by taking f prime at x. We'll just go left to right and differentiate this one. This one's coming out as a 6x squared minus 18x plus 12. We got it, folks. That's our derivative. We could leave it like that and set it equal to 0 and solve, or probably even if you set it to equal to 0 and solve, you have to simplify this. Might as well do it right here. Well, we like factoring, so a 6 can factor out of everything. That's always a good first step. Factor out a 6, and we're left with x squared minus 3x plus 2. That makes the further factoring we have to do right here much easier after factoring out a 6. This turns into 6 times. It'll be at x and an x. Because of positive here for the constant term, we need positive in the middle of both of those groups. We're trying to get to -3 using factors of 2, but 2 is prime, so it's great. I'll put I put pluses there. That was almost right. Well, the signs have to be the same if this is positive, but what's the correct signs? Yeah, they have to both be negative. If I put a 2 here and a 1 here, well, that's x, that's 2x. They do not sum to 3x, but we don't throw the baby away with the bathwater. We just go back, change these signs. Now double check. That's -x. That's -2x's. And so we have hit the -3x we have to target. Whenever it comes to doing these in an exam setting, sometimes there will be factoring like this, but I'm not going to try to give us the nasty factoring problems unless it's in homework, and the homework, they can be harder. Sometimes they might need quadratic formula as we've seen, but for exam purposes, it's got to be a little bit faster because this algebra is not the main takeaway for those kinds of questions. It's more the calculus. So I would say this is a pretty standard exam type question in terms of difficulty as well. Well, we've got the derivative calculated. It's in its most simplified form. So now to get the critical numbers, we take the derivative and set it to 0. I'll write this just to connect it with the notes. We're pretty much just taking 6, x minus 2, x minus 1 set to 0. But you could have just read them off right where the red dot is. You get a 0 when you plug a 2 right here. You also get a 0 when you plug a 1 right here. So those are the critical numbers of f. I'll write crit for a critical number when we refer to it, just as a shorthand. So we have 2 critical numbers, and that means when we go to solve this problem, we're pretty much doing, once I get these things in the right spot, we're doing this right here. We need a sign chart to organize all of the information. The values where things get cut up, they're the critical numbers. Sometimes we just call them cut points. So here's what I would do next, right at this stage. We draw a real number line. I like to put infinities on mine in case that's part of the interval that I'm going to be putting in. So negative infinity to the left, positive infinity to the right. Take your critical numbers and start placing them. Here's what 1 will be, 2 will go here. Next, let's use our brackets. I'm only using brackets to say that the value of the derivative, f prime, well, it's either going to be positive or negative here, from 1 going to the left on negative infinity, and it can never actually become a different sign. If we say it's positive here, it stays positive because the only way it could ever become negative again is if there was another critical number setting the derivative back to 0. So these are the only places where the sign of the derivative stays the same in those same 3 regions. Next thing I would do is, let's go to this pen. This is now scratch work. I need a test value to figure out what the sign must be right here. Easiest test value would be 0, and we can say f prime at 0. I'm plugging a 0 in this form where it's unfactored. That gives us a positive 12, which is greater than 0. So now we know once and for all, the first derivative is positive in this region from negative infinity all the way to 1, where it takes a value of 0, where it's a critical number. Now, looking back at this, the multiplicity of 2 is 1. The multiplicity of 1 as a 0 is also 1, because the powers on these groups are 1. That means I expect all of these signs to flip. But to be completely honest, I would probably still test it out. That's just a shorthand once you start seeing some patterns on this. Oh, less than 0 on that one. So let's test out 1.5 and make real sure it really is a negative derivative, that f prime is really less than 0. So we're testing f prime at 1.5. Note we're indicating it as f prime. We're not putting these values inside the original function f at all. We're just testing the sign of the derivative. So 1.5 is going to go here. Now it's much easier to use the factored form rather than the unfactored one. We can go 6. 1.5 minus 2 is going to be negative 0.5. 1.5 minus 1 will be a positive 0.5. And we don't even really need to know the value of this number. We just needed its sign. It's a positive times a negative times a positive. So this thing is negative. All right, less 0. And double checking, yeah, we said less than 0 right here. We're on the right track. Let's test one more just because we can. Let's see what happens with a 3. We'll place a 3 in the factored form and say the derivative of f at 3 is 6 times 3 minus 2 for a 1, then 3 minus a 1 for a 2. That one's positive, so we put positive right here. Now all we have to do is summarize. First, before we go to our conclusion, any questions or comments at the moment? Okay, so to summarize, we cranked out the derivative, we set it to 0 and we solved it. We found 2 critical numbers, and all we've done is test the sign of the derivative at each one of these intervals. But now the increasing decreasing test can be used. Let's say here for our conclusion, f, we're referring to this function now, not its derivative. That original polynomial f is increasing on anywhere where the sign is positive. So it'll be increasing on negative infinity to 1. Union, from here it'll go from 2 to positive infinity. So that's our first conclusion. And we can say next, it's decreasing in this region. And f is decreasing on the region from 1 to 2. So that concludes the decreasing increasing test. We now know roughly what the shape of the graph would look like just based off that sign chart. Well, we did it, folks. We now need to find the local maximum and minimum values of this function. But really, all the work in finding those values is pretty much all right here. This is what I would do when I go to part B. It's really just summarizing at this point. Let's take a look at this value right here. We need to find whether this is a local maximum or a minimum, but it's increasing to the left, decreasing to the right. So the curve would have about that shape. It increases and then decreases, and it peaks right at 1. That's the picture of a local maximum. And so I would go back over here and write f at 1. Now this is the tedious step. We have to actually put this in a calculator. This is going to be 2 minus 9 plus 12 minus 3 after putting a 1 in there. So that's going to be a value of 2. Then go back to the sign chart. It went from increasing to decreasing. So this too is a local maximum. I'll just say local max for short. Does that make sense to folks on this one? Okay, if this formula was a degree 2 polynomial, we could have done the same work. We would have taken the derivative, set it to 0 and solve. But what we would have really discovered is the vertex formula. We would find the vertex of a parabola if it was degree 2. But now we can redo all of the same work for any degree polynomial. This could be degree 50 and the same method applies, just the same. Let's now finish off this portion. I'm going to delete these little decorations I put on the graph. They're just mainly for visualization. We don't want the graph to get too busy. On the left here, it's decreasing, so it begins like this. Right at 2, it has a horizontal tangent, so it levels off here. But then it turns around and starts increasing again. So I expect the shape of the graph to look like this. That means a local minimum. So f of 2 equals, that's not as friendly. This is why calculators are allowed on this exam in case this is the function on there. Let's grab a really fast one. We're placing 2 inside this function here. Now, honestly, the best way to do this, if you're using Desmos, is just to define the function. Minus 9x squared plus 12x minus 3. So there's the function. Now I'll just use ordinary function notation, evaluate f of 2. This comes out as a 1. On a real exam, you would just have to crank this out with a calculator to get a value out. But here I'll just say this came out as a 1. Double check. That's a local minimum at this value. Is a local minimum. So that's the whole procedure, folks. Any questions or comments about it? Okay, so finding minimums and maximums. If it's a polynomial, this is pretty much how the work goes. If it's some other function, pretty much the same thing. You would take the derivative, set it to 0 and solve. Like we mentioned before, that's pretty much how majority of these problems are actually starting. But another tool that's available to you when you're learning this topic, definitely take advantage of a graph since, I mean, if this is a homework problem rather than an exam question, you might as well use any tools that are available to you, and this is extremely powerful. Let's check out our work. I would encourage you to try it first purely by hand. Try not to rely on the graph. Think of this as being an exam problem and write it out that way. But then once you're at your end, let's see how we did. Here's a local maximum, and the local maximum is 2. We can't give it as a 0.12. We have to commit to 2 itself. So make sure not to write your answers as an ordered pair. The actual maximum is this 2 we put on paper. But it matches up with that second coordinate, so we're in business. This one's a local minimum, and the value is 1, like we said. So yeah, we've got the right picture here to match the work we did above. Well, any questions at all, folks, on getting through this one? Okay, let's take a screenshot on this just so that it's apparent on our paper here. And that's the process of finding local minimums, local maximums. You don't have to include a graph, just here for reference. Well, after dealing with maximums and minimums, we want to change gears a little bit and talk about concavity. Once I get that to come back up. Concavity to me was always kind of a tricky concept. Before we actually do any real calculus on it, these are just ordinary definitions. This is just the geometry of what we even mean when we say concavity. We could let this graph right here serve 2 purposes. It was our check on the last problem. And let's let it be part of our description of what we even mean when we say concave up versus concave down. So here's our definitions. We'll say if the graph lies above all of its tangents on an interval, we are concave upwards. That's a confusing definition. It says next, if it lies below all the tangents, it is concave downwards instead. So to get a feel for this, we're pretty much forced to draw tangent lines all over this curve, or else it's really hard to see what this is saying. Notice tangent lines have really just been par for the course in a lot of these kind of problems, understanding what they look like, how to sketch them, and so on. So let's start sketching a few. I'll just do little dashed lines. I like putting tangent lines here where a local maximum or minimum would be. Notice right where the red dot is right here. Would you say the curve is below or above its tangents? Turns out it would be below on the tangents on this one, but by this red dot right here, it would be above its tangents. Let's put in some more tangent lines. We go, say, put more going this way. They would come in like this. More come in like that. And it looks like no matter where I put a tangent line on this segment of the curve, let's say we put one here. This one's kind of tough to draw. It looks like the curve is always below. Would you all agree with that? Awesome. Let's put down. Well, that's kind of hard to erase, actually. I just didn't want the diagram to get too busy. We know that if it lies below its tangent lines, we have concave downward. So it looks like from here to here, well, it's hard to say exactly, but we have concave down. But there's a weird point somewhere. When we draw these tangent lines, this is why it's concave down. The curve is below it. But if we draw these other tangent lines, suddenly the curve is above it all of a sudden. There's a transition style point where it changes from concave down to concave up. And I can't quite get my bracket right until we try to find it. So let me back off of this just a little bit. We'll come back to there. Oh, didn't mean to scribble on it. Let me try again. And let's zoom in just a little bit more and see if we can see where the transition point is going to be. So once again, you can draw all these tangents. The curve is above it, but somewhere around here, a tangent line goes through. Say, maybe it's right in this location. If I draw a tangent line here, the tangent line kind of looks like this. On one end of that same tangent line, the curve is below. On the other end of the same tangent line, the curve is above. We call that point the inflection point, where it transitions from concave down to concave up. So on our graph right here, hope that's zooming out too far. That's our transition point. I'll just label it as a point C. So now from all the way up to C, I'll draw this just slightly different so we can see it better. From here all the way to C, and my bracket has to convey, this has domain all real numbers. So I'll kind of go like this. From here all the way over to C, we're concave down. Let's put in those tangent lines once more. I'll just do the horizontal tangent lines to show it. Curve is below its tangent. But if we go, say, to the right of C, here's this tangent line. We have concave up. The curve will always be above any tangent line you draw in this region. So we'll say it's concave up. And the transition point, we say, is a point of inflection. It's right here. The inflection point is C, comma, F at C. So that's the situation when it comes to concave upward, concave downward. We have to visualize tangent lines if we're doing it as a graph. And the inflection point is extremely hard to find on these kinds of graphs, but that's okay. We can still work with this. And when we do it with, say, a function like this one, we're going to be using the concavity test instead. But let's still pause on this for a little bit more. I think these are pretty tricky concepts. Any questions or comments about concavity at the moment? Okay, let's maybe draw one more curve that attempts to say, what do we care about concavity? What is it doing for us? My curve is going to look like this. So another function where everything is in quadrant one. And I want to draw my curve starting right at the origin. And it's going to increase in kind of a strange way. It's going to do this. But then it's going to do this. Let me think about this curve. These are slightly challenging for me to draw. Let me try one more time at this. That could be our curve right there. Let's say that this is something like time. So the variable here might be t. This might be population. So this would be a function, y equals population at time t. Now let's see if we can find the inflections on this one, or not the inflections, concavity first. If you're on where the red dot is right here, what would you all call that? Concave up or concave down? I agree. Let's put a tangent right where it is. I was about there. And honestly, I have a trouble kind of seeing this myself. The only way I get through it is I literally draw the tangent line and then suddenly my eyes see it. The curve in black is below the tangent. It must be concave down here. Now, let's go over here. It's concave up somewhere in this location. We can see it with the tangent line. Inflection point, always a big challenge. I'm not completely sure where it is, but I would guess it's about right here. So here's our point of inflection. Oh, geez, that's the wrong color. Let me try again. Inflection point. And now that we have all that on, here's what I want to add to this graph. Oh, I guess we still have to talk about concavity. So from here to here, we have concave down, and it looks like from here to here, concave up. So now back to the curve. When we look at this curve, concave down versus concave up sometimes is conveying certain information about this. When it was concave down, it was increasing extremely rapidly, and then it began to level off until we got to this inflection point. So we had rapid growth here. We hit the inflection point and concavity switched. Now here, it's still growing, but now the growth rate is reduced at this point. It starts picking up here, but after we get to the inflection point, that's only when it begins to start picking up once again. So we had rapid growth beginning to level off, then rapid growth once again on this curve. Well, any questions about these drawings so far? Okay, so that's concavity. We have a couple pictures here just to kind of visualize it. But however we visualize it, try drawing lots of tangent lines, maybe in pencil, so your book doesn't get too busy or anything like that. You'll have a good feel for what's what in these cases. But let's take a look at the test now. Doing this visually is really very, very hard. There's almost no way I'm pointed to the right location of this inflection point. I can never tell you exactly its value. But if we use calculus, you absolutely can. Calculus is going to give you the coordinates of the inflection point immediately. And when we solve this problem, the big takeaway is this should feel almost exactly like you're doing this problem. The only difference is we're going one derivative higher. We still do a sign chart. We still say the sign of the second derivative, not the first one. We convey the information about concavity and it finishes off the problem. So the concavity problem is essentially the same as the increasing, decreasing local min, local max problem. Let's give it a try and see how it goes. Here's the concavity test. Now, if we have something concave upward, that means it lies above all its tangent lines, but it also means the second derivative is positive on this function. Likewise, concave down just means second derivative is negative. And I really like these directionalities. It makes sense. Positive for upward, negative for downward, but these things get reversed in the theorem that's right below this. So watch out for that. The directionalities don't always go in the way we would like in this problem. Well, let's give this a try. We have a brand new function. It's the natural log of x power 4 plus 27. We want to know where this function is concave up, and we want to know where it's concave down. Then we'll find the points of inflection. So this is synonymous with increasing, decreasing. Inflection point is synonymous with local minimum, local maximum when we did that problem. But the first thing we have to do is, let's take a look. We don't take the first derivative, set it equal to 0 and solve. If we're doing these two inequalities here, here's what we really need to do. To solve this, it's an inequality about the second derivative. That means first, solve f double prime at x equals 0. That's analogous to the critical number step. In fact, we are finding a critical number, but it's not a critical number to f. It'd be a critical number to f prime instead. So that's our first step. That means we have some derivatives to calculate. This one's a chain rule. We'll do the natural logarithm first. That's the outer function. When you differentiate the logarithm, it's just going to throw it down to the denominator. Then we multiply by the inner function derivative second. And if you wrote it down in just one line, then again, that's excellent. That's kind of the goal with seeing these, the ability to just see the function and write it down. What goes into the denominator is x power 4 plus 27. That's also what's being differentiated. And so this combines as this format in the answer. X power 4 plus 27 and a 4x cubed. So there it is, folks. That's our first derivative. But in the concavity test, we need this first derivative only so we can get to the second derivative. We're not solving this one set to 0. Instead, we move over to f double prime. So our problem started as a quotient rule, or excuse me, it started as a chain rule. Now it's going to turn into a quotient rule at this step. So as we calculate this one, first we must differentiate the numerator. That's going to be our 12x squared. Multiply that by x power 4 plus 27. And I never make these fraction bars long enough, it seems like. Then minus, now copy in the 4x cubed. It gets multiplied by the derivative of that denominator. We've done that once, that's 4x cubed again. Then down below is x power 4 plus 27, but now it's raised to the power 2. So we've got a second derivative, but just like when we did in chapter 2, we never stopped here. We have to start simplifying as much as feasibly possible. And this time we're doing more simplification than chapter 3 because now we have a purpose. We're solving that equation. And that means lots of factoring, lots of simplifications. So here's how it goes. I'd probably just start by expanding out the numerator. Distribute 12 inside, and I'm going to need a calculator for that, but it's going to be 12x power 6 to start. Now I need to take 12 by 27. Way too late in the week to do arithmetic. Let's do it this way. We get a 324 on that one. So plus 324x squared. Over here, we're getting negative 16x power 6. And once again, whole thing divided by x power 4 plus 27 quantity squared. So there's where it sits so far. We now have like terms we can combine. So let's write this as 324x squared. We have a 12x power 6 minus 16 of the same thing. So altogether minus 4 x power 6. Then the whole thing is divided by x power 4 plus 27 squared. So that's where the function sits. Now we have to set this equal to 0 and solve, but we could still work with the numerator if we wanted to. Honestly, I think for this problem, it might be better to just set it equal to 0 right now. That way, we're never copying the denominator. It's just a little bit less writing. So let me do this right here. We're doing Just need a different color. I wanted to keep these two colors the same. We're now doing f double prime of x equals 0. The only way that's possibly true is if the numerator is 0. So that would be 324 x squared minus 4 x power 6 has to be 0. Does that make sense to folks on this line right here? Awesome. That's the great thing about rational functions. Set them equal to 0, and this is all you ever have to worry about. Kind of nice in a way. But then now we have to worry about that, so let's work on this function. Now, the things we can't do is add 4x power 6 to both sides and divide by x squared or x power 6, because x equals 0 is a potential solution to this. We'd be throwing away even more solutions if we did that. So instead, let's just factor this. That's our go-to method. I know we can factor out an x squared. That's the lowest power that appears in both of these terms. My hope is we can factor out a 4. Let me test that out. Awesome. Do you see how many it goes in? Awesome. Thanks for checking that out. So let's factor out a 4x squared. And 81 here minus x power 4 right here. And all that is set equal to 0. I'm running out of space to see the concavity test. Let's put it down below for a moment. Okay, so that's where we're at so far. But now it's factors even more. We have a difference of squares. 81 is 9 by 9. X power 4 is x squared by x squared. So on the next factoring step, it becomes 4x squared. And let's go 9 plus x squared, 9 minus x squared. So difference of squares always factors in this nice way. This one is a sum of squares. It's impossible to factor this one. And the only way you can make this be 0 is if you're using like 3i, complex numbers. So that's okay. We're only dealing with real numbers. But that one splits up some more, right? This is 3 plus x, 3 minus x, right? Let's put that in. So 4x squared, 9 plus x squared. Oh, and this is a 3 minus x, 3 plus x is all set equal to 0. From here, we can just read off the numbers. Where that x squared is, we'll say x equals 0. Multiplicity is 2. I'm putting down the multiplicity only because it came from power 2. And this is just a way to get through the sign chart in a slightly faster way. You don't have to mention it if you don't care for that. But let's now go off to this one, x equals 3. This has multiplicity 1. And final one, this concavity test has to go way down there, I think, is negative 3 on this term. Multiplicity 1. So we effectively have all of our cut points. We would have called these critical numbers, but we took a second derivative. They're truly critical numbers to the first derivative. It's almost better to not even mention that. That becomes more confusing than it's worth, I'd say. But once we find critical numbers, the immediate next thing we do is we write down a real number line. So here it is. Actually, I want to make sure I have enough space to show everything. Let me put it over here. Here's our symbols. I was about to put negative infinity on here, but that's actually a mistake. Let's take another look at our function here. Well, is it a mistake? I knew there was a natural logarithm, so I was definitely concerned. But in our natural logarithm, you can put any real number inside that. The x power 4 is what's saving us. Natural logarithm cannot have a negative number, but if you ensure its input is always positive, the domain is all real numbers. Let's take a look at that function just to validate our intuition on it. F of x is the natural log x power 4 plus 27. Weird looking curve. Its domain is all real numbers. So yeah, we're okay right here. That was me just worrying more than I needed to. We're okay here, but it's definitely something to watch out for. Some of these functions could have domain issues. Now let's put on the values. We have 0, negative 3, positive 3. That means the second derivative is partitioned into 4 different regions when we made 3 cuts. So we need to find the sign of the second derivative here, 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 and here. We just want to put greater than or less than on every one of these regions. That means we have to do test points, and that can get pretty tedious on these kinds of problems. This one would be way, way out of bounds as a real exam question. I'd have to simplify the function a lot for us to get through it, but it's definitely par for the course for a homework problem. Here's our second derivative right here. And as a homework problem, really great idea to take advantage of the calculator this time. So I'm going to hide this function. Let's put in the second derivative. Well, actually, I think I actually have to delete it actually, if I'm going to work with it that way. So f of x, think of this as, I'll write d2f to say it's the second derivative. It's 324x squared minus 4 x power 6. And the whole thing is divided by x power, oh, that needs a parenthesis, x power 4 plus 27 squared. So that's our function. Did it even plot? Oh, they don't know what the D2 means on here. Let's just call this, I'll just call it generically f of x, so it's not too concerned. That's what the derivative looks like, kind of an interesting function. But all we care about is the sign. So I'm going to pick a test point here. Let's try out -4. F -4 comes out as a negative quantity. So what I would write down immediately is less than 0 on this one. So 1 down, 3 more regions to go. Now let's look at that -3. It had multiplicity 1, so I'm going to make a prediction here. Across a multiplicity 1, the sign will flip. Now look at 0. This one's at multiplicity 2. At an even multiplicity, this one, the sign is the same, but we should check that out. At 3, multiplicity is 1, it's odd, so it should flip our sign. So that's just a time-saving step, but it's good to be really sure. So let's try it out and see if we really have it. I'd probably pick -1 for this region. At -1, we have a positive value, 0.4081. That means the second derivative was positive. So move over to this region, +1. I broke the function. Let me try it again. Oh, where'd that one go? Same value, it's positive. There's lots of symmetry in this function. In fact, we're seeing the symmetry here. At -1, we pick a value. +1, we pick the same value. It's all because the 0 at 0 was a multiplicity 2. That's really the only reason on this. And it was multiplicity 2 because of the x squared. So yeah, that stays positive here. We test a value at 4, it flips back to negative. So it went negative, positive, positive, negative. Now, what was the instructions on this one? It's easy to forget. Find the intervals where it's concave up, and the intervals where it is concave down. All we have to do is look at the sign of the derivative, and directionalities are great. Positive for up, negative for concave down. So now we're ready for our conclusion. Let's say, therefore, f of x. We're returning to talking about the original function because we're talking about its graph when we say concavity. F of x is, I'll start by saying concave down. It goes from -infinity to -3. And we had another one section that's concave down. This was from 3 to +infinity. So 3 to infinity here. And f of x is concave up on now this concave up is really super tricky. It's not from -3 to 3. That's really weird. Right at 0, the second derivative is 0. It doesn't have concavity there. That's the transition point. Well, excuse me, that one's not even a transition point because concavity never even changes. So this one is really, really technical. If you did give me from -3 to +3, I'm not super picky on that, but I probably would put a note on it. It really needs to be this. -3 to 0, union 0 to 3. That 1 point right here is excluded when we talk about concavity, but that's just the same as increasing, decreasing. Yeah, go ahead. It would be differentiable at that point. If we look at our original graph, it was not this nasty function. F of x equals natural log x power 4 plus 27. And right at that location, we had a nice point right here. Essentially, all that's happening at 0 is, well, it's concave up here, lose concavity, the second derivative is 0. That's all that happened. And then concave up again, or let me double check, concave up again right here. Yeah, that looks about right. Really kind of weird, but again, the analogy is still this problem. Right at 1, for example, it's neither increasing nor decreasing. And that's why we had to make a cut right here. We threw a 1 out of the increasing set. We threw 1 out of the decreasing set at the same time, similar to what's happening to us on this problem. Well, other questions, folks, so far? Yes, exactly. Good call, absolutely. I don't have a technical term for what's happening on this one. It definitely has concave up here, but right here, really the thing that I would say is it just doesn't have a sense of concavity at all at that one spot. It'd be like when we drew, where is it? When we went over here at that inflection point, well, this one's not an inflection point either. So it's just a very odd point. Maybe another way to think about it is, by analogy, it's kind of like this that's going on, where we found something interesting. We found that the derivative was 0, but it's like it's increasing on the left, increasing on the right. It's basically this situation by analogy. There's a point where nothing happens. There's no maximum, no minimum. And just like with concavity, there are certain points that just have no notion of concavity, and they're not an inflection point either. But does that answer your question about that? Gotcha. Mm-hmm. Other questions so far? Okay. Well, again, that is a really good thing to take away from this. An inflection point is only when we change concavity, and it actually has to be a point on the graph. So if -3 was relative to a vertical asymptote, it is not an inflection point. It's not even a point on the graph. So when we go to answer this last portion, let's definitely, for part B, pull in the definition as well. This is pretty tricky and technical. Here's the definition we're using. Okay, back down to this graph. It says find the points of inflection on the graph. And here it changed from concavity of concave down to concave up. So we can say -3, f of -3. We'll have to find out what that is. And the other inflection point is, well, it's not here. It's concave up to concave up, which means concavity never changed in one way or another. So we have to skip past that point. We can't talk about 3, like you said. It's 3 f of 3. And so the inflection points go, well, I need to remember what f of x even was. Again, that's what's kind of tricky about this problem. When it talks about f of -3, we're referring to the original function. When we're running through the test, we were using the second derivative. But now back to here, just for quick reference, this becomes -3 natural logarithm of, it's definitely a calculator worthy. Let's put 3 or -3 here. Yeah, go ahead.
So is f of -3 and f of 3 the same value?
Is f of -3 and f of 3 the same?
Right.
Yes, it would be. It's all because of that power 4. It's going to kill off that negative. And that's the reason it's coming out the same. So we'll get f of 3, f of -3, exactly the same, just as you said. And let's see here. Let's see if we can do this in a slightly cleaner way. Let's put either -3 or +3, power 4 here, plus 27. We get 108. And so this is natural log 108 here. And this one is +3, natural log 108 right here. That means we did it, folks. That's the conclusion on this one. Just like on the prior problem with local mins, local maxes, this is the hard stuff, bringing down the sign chart, analyzing the intervals. But when it asks for inflection points, that's really fast. You're just making conclusions based off your prior work at this stage. Well, we did it, folks. This is the conclusion of the notes so far. Any questions or comments at the moment? Okay, I'm looking at the time that we have, and with the time that we have just enough time. Don't worry, the second derivative test is still up there. We have just enough time to describe this problem, but unfortunately, not enough time to conclude it. So I'm going to make some edits onto the Moodle website. I'm going to change this assignment here, and I believe 29 and 30 are just the ones I can't get to. I'm going to leave them on the assignment. Let's just make them extra credit. We haven't done that in a while. I'll call these both 5 points extra credit. So that's what we're going to do right down below here. Use a second derivative test to find all local maximums and local minimum values. Oh, that's what I was deleting over here. I thought I deleted something else. Sorry, let me get this back in line. So at the last of our time, I want to show you what this test looks like. I don't have enough time to put down a problem and solve it, but I will put it on the notes and upload it later on. And that way, if you decide to go for those extra credit questions, you'll have a guide to go through on how it really works. And by the way, for those extra credit questions, I also said you only have to use the second derivative test. The author asked you to use both to compare methods, but you are doing plenty of first derivative test and there's other things here. But first, let's look at the concavity test, show what it looks like geometrically, and then we'll call it a night. Notice how weird it is first. It says, if the second derivative is positive, you have a local minimum. That just looks like a typo. It says here, if the second derivative is negative, you have a local maximum. Now, how in the world could that be true? We need a curve. Let's grab it. I think the best curve for this would be this one once again. It has a minimum and a maximum. Let's see just what in the world is going on right there with this test. It's an extremely powerful test, so even though we're not doing these extra credit questions, we'll start to look at this test in more detail in class once we're in the optimization section. So here's how this is going to go. First, take a look where it says f double prime of c is bigger than 0. Well, if f double prime of x is bigger than 0 on an interval, f is concave up. This is the one that matches the directionality. So let's look at where we have a local maximum. Or hang on, if the second derivative is there, it's concave up. Yeah, I think we're great. Let me draw some tangents generically. Maybe on this one right here. And on this one right here, I'll just do the horizontal tangents. So on this one, which is a local minimum, would you call this concave up or concave down? Exactly, this one is going to be concave up. And let's take a look. When the second derivative is positive, that's concave up, we'll have a local minimum. That is really weird, right? It's actually correct as a statement. Concavity is helping you find local minimums and local maximums as well. So if we stay concave up on that critical number, you get a local minimum. Likewise, this value here is a local maximum. It's concave down in that region. F double prime of x less than 0 on an interval means f is concave down. So it matches its directionality here. But right here, this is a local min, or excuse me, a local maximum. Regardless of the fact the second derivative is negative in that region. So it's unfortunate that the concavity test, and the second derivative test, they ultimately give us conclusions that are correct, but they could hurt your brain. They look backwards, they kind of look wrong. It's the right conclusion. So if you're going to use this test, here's the steps you have to take. Notice what's highlighted in yellow here. The very first thing you do is compute f prime of x, or let's say it this way, solve f prime of x equals to 0 to get critical numbers. So that'd be the very first thing that you would have to do. That would be what we would do if we had time for this problem. And that's a portion right here in yellow, find critical numbers right away. This is not like the concavity test where we set the second derivative to 0. Then on step 2, evaluate f double prime at the critical number c and just check its sign. If you have positive, you're getting their local minimum. Negative is a local maximum. But some curves, even when you have a critical number, there's no minimum, no maximum. And that's what happens right here. If it ever happens that the second derivative is just 0, much like when we didn't have an inflection point, even though it was concave up across two locations where it was 0, here, the test just falls flat on its face. This happens when essentially your curve, once again, looks like this one here. There really wasn't a local maximum. Well, any questions, folks, with this geometric outlook of this test here? Okay, this will be our stopping point for the class then. And just a reminder, I'm going to put this on the notes. The problems 29 and 30 are for extra credit. Well, have a great night, folks. And congratulations, we got through midterms week. The week after, I think things should probably be kind of going back to normal on most people's schedules. If you have questions, I'll be happy to help. Otherwise, next section will be in 4.4 with L'Hopital's rule. We'll be taking more and more limits.
So 100% got concavity, so this should be concave down the white line, right?
Yeah, I agree with you on that.
And
Yeah,
then if I draw that blue line, because the curve is below the blue line.
you've
then
got
it's
concave down. Yeah, exactly.
And then the way I know it's not concave up is because I draw that green line and it crosses over the white line, right?
Yeah, I like that. Absolutely. That's a great way to, a great outlook for that.
Well, thank you.
I was able to finish the assignment because assignment due today. I turned later on tonight.
I'd be okay with that. Yeah, absolutely.
Thank you
And
much.
here you go. I've been meaning to get that to you.
Thank you.
If I could get to you, I'd probably just scan it and email to you. Would that be okay as well?
What's my message?
If I couldn't have gotten it to you, I probably would have just scanned it and emailed it to you. Would that have been all right with you as well?
Yeah, it's fine.
Okay, gotcha.
Thank you.
Yep, have a good one.